Hi all, we are continuing in chapter 6 now, so still in thermochemistry. So this topic we're going to go into is using the general properties of reaction enthalpy. So we saw enthalpy originally in parts 1 and 2 just briefly. We're going to go into enthalpy more now. And as a reminder about the types of calorimetry we've gone through so far, we do have constant pressure calorimetry, which we associate with a coffee cup calorimeter. Then I did introduce the idea of constant volume calorimetry. This is bomb calorimeter. This uses a bomb calorimeter. So in bomb calorimetry, we're going to do an example of bomb calorimetry style problem a little bit later. So I introduced this. We practice using the coffee cup calorimeter style problem, and we are going to do an example with a bomb calorimeter style problem. And depending on the specific heat of the calorimeter itself, sometimes this is introduced into solving for heat of a specific reaction. Sometimes we just consider the reaction and the water that surrounds it. Then again, depending on the material of the calorimeter itself, sometimes we also include this notion of the heat of the calorimeter involving the specific heat of the calorimeter. And remember, due to conservation of energy, and heat is a form of energy, no heat, no energy can be created nor destroyed. So it needs to net out to zero. We can't have the heat of the system be magically 5 kilojoules, for example. It has to come from somewhere. So for the heat of the reaction, again, if we do incorporate the calorimeter, then we have to incorporate water and the calorimeter to get information about the heat of the reaction specifically. This is what we're normally interested in, is what's happening in the specific reaction. Then this formula we've used a few times now, so Q equals mcat, where lowercase s and lowercase c are both the specific heat capacity. So both these specific heat capacity, and what are the units of a specific heat capacity again? Well, this is joules per gram degrees Celsius or joules per gram Kelvin. The important variable in here is the mass. So specific heat capacity, we get specific as a way to remember it. We're going to incorporate the mass of the pure substance in a specific heat capacity. So the energy per 1 gram per 1 degrees Celsius or per 1 Kelvin. Then I mentioned briefly that enthalpy is a way to think about the energy of a reaction. In calorimetry, if we're just assuming that heat is the only factor for energy, then the heat of the reaction is equivalent to the enthalpy of the reaction. And this holds when we're at constant pressure. So if we did something to increase the pressure of the system, like add more gas or heat up the gas, then pressure would not be constant and this relationship would not hold true. And again, we're going to go into this enthalpy idea a lot more today. And previously we did use this equation to solve for the internal energy of a system. We looked at the heat of the system and the work done on the system. We also used this equation as well, where work is proportional to negative pressure times delta volume. Now again, if heat is the main form of energy that we're interested in, then we can equate heat to the change in enthalpy. Then work is still defined as the negative pressure times delta volume. So this equation incorporates internal energy and enthalpy. You won't need to worry about plugging anything into this equation or solving for anything. I just wanted to show you that the internal energy of a system can be connected to heat and work, like we saw previously. Then we can also incorporate this idea of the enthalpy of the reaction, because we think of this ultimately as the energy involved in the reaction, where the energy involved in the reaction can be equated to the heat of the reaction. Then we saw this visual as well. I want to clarify that if the change in volume is increasing, so let's say the gas is expanding. If the gas is expanding, the gas is doing work. Then if the gas is decreasing in volume, it's being compressed. then work is being done on the gas instead. So the gas expands, it is doing work itself. If the gas then is being compressed, then work is being done on the gas. And I'm saying gas here as being our system. So again, just wanted to introduce you to this equation. I'll go into a lot more detail on enthalpy and why it matters for us. So the formal definition of enthalpy, we know we really think of this as the energy. Formally, enthalpy is used to quantify the heat flow into or out of a system in a process that occurs at constant pressure. So enthalpy we think of as energy in the form of heat flow. Enthalpy we represent as capital H, so then that change in enthalpy is denoted by that delta or triangle out front. So this would be the change in enthalpy. For the change in enthalpy, we're usually thinking about before the reaction and after the reaction. So what was the state of the system before the reaction and then the state of the system after the reaction? So because of that, then we can say that the change in enthalpy involves the enthalpy after the reaction or the final state minus the enthalpy before the reaction or of the reactants. All right, so we have our reactants going to products. To find the enthalpy change of a reaction, we want to look at the enthalpy of the products minus the enthalpy of the reactants. So still final minus initial, but now final we think of as the products, and initial we think of as the reactants. In most scenarios we're going to deal with, we will be at constant pressure, but again, enthalpy is the change in enthalpy, delta H, change in enthalpy, heat given off or absorbed during a reaction at constant pressure. Generally, when we're working with enthalpy, it'll be an assumption that we make that we're working at constant pressure. So we have seen these signs here for endothermic versus exothermic processes or reactions. Now that we are formally connecting that the enthalpy change, the change in enthalpy, is products minus reactants, let's talk about what the sign would be for an endothermic process. Is the energy or the enthalpy higher for the reactants or higher for the products? So reactants start out at some state for an endothermic process. We know there is an absorption of energy for an endothermic process. If the reactants absorb energy in that endothermic process, the products are going to end up at a higher energy and a higher enthalpy. So if we're finding delta H for an endothermic process, let's say arbitrarily the enthalpy was maybe 1 and then 5 for the reactants and then for the products respectively. Delta H, the change in enthalpy, is the enthalpy of the products, so a larger number, minus the enthalpy of the reactants, so a smaller number. That means that always for an endothermic process, the sign of delta H is going to be positive. In an endothermic process, the reactants are a lower energy or a lower enthalpy than the products. They absorb energy throughout the reaction in an endothermic process. So again, enthalpy of the products is higher than the enthalpy of the reactants. That's how we get a positive sign for delta H. Right? So if delta H is greater than 0, it means it is a positive sign. Let's do the same for an exothermic process. We know for an exothermic process, our reactants give off energy. They release energy at the conclusion or by the conclusion of the reaction. So the products are at a lower energy or a lower enthalpy than the reactants because, again, they give off energy over the span of the reaction. The reactants are going to be higher energy than the products that they end up as. So enthalpy of the products is less than the enthalpy of the reactants. By taking delta H as the enthalpy of the products, we can again say this is an arbitrary enthalpy value of 1 and then maybe 5. So then products minus reactants, this is a smaller number minus a larger number. So this enthalpy, change in enthalpy for an exothermic reaction is always going to be a negative value. So it's going to be a negative value less than 0. For an endothermic process, it's going to be a positive value greater than 0. Okay, so endothermic process, heat is absorbed by the system from the surroundings, so the change in enthalpy from reactants to products is a positive value. And I'm sort of using enthalpy, heat, and energy all interchangeably here. We remember that heat is a form of energy. For an exothermic process, the two reactants form a product, two products at constant pressure. The reaction is exothermic. Heat is released by the system to the surroundings. Therefore, the change in enthalpy from reactants to products is a negative value. The reactants are at a higher energy or enthalpy than the products because heat is released throughout an exothermic reaction. So a smaller enthalpy minus a larger enthalpy, that's going to be a negative value for delta H. So endothermic, positive delta H, exothermic, negative delta H. And because this concept of the sign of delta H is so crucial, here's a whole slide on endothermic processes and the positive sign for the change in enthalpy. Heat is absorbed by the system from the surroundings for an endothermic process. Therefore, from reactants to products, delta H is a positive value. And again, technically for enthalpy, it is important to note these take place, or we get these enthalpy values at a constant pressure. So let's talk about the units then for delta H. Typically, we see units of delta H in joules per mole or kilojoules per mole. So if we see a reaction and we are given a delta H, it's a positive value for delta H. What can we take away from a positive value for delta H? Well, now we could look at this and know it is endothermic. Without knowing anything else about the reaction, we see a positive delta H, endothermic. And what does it mean if it's on a per mole basis, right? So this is how many joules of energy per mole. If you're given a delta H and it's in a kilojoules per mole, you should read this as for every 1 mole of ice that melts at constant pressure and at the melting point for ice or water, 6.01 kilojoules of energy or heat are absorbed for every 1 mole. What does this mean for us and what we've seen before? Well, a big hint is that we have a per mole basis. We can start to think about stoichiometry. So this is a 1-to-1 mole reaction. If we had something like 2 moles of H2O solid go on to produce, can keep it simple here, 2 moles of H2O liquid state, then there are 2 moles of H2O solid here. That means the total enthalpy for 2 moles is this number times 2, right? Because this is how much energy for every 1 mole. And if we have 2 moles, then we'd have to multiply this by 2. Again, though, these are reported on a per 1 mole basis, but we could apply this, for example, if there was not a 1-to-1 mole ratio. Now, the same thing holds for exothermic, reported in kilojoules per mole. If you saw a reaction, it's at constant pressure. You didn't know anything else about the reaction except this negative sign for the change in enthalpy. You can immediately think, okay, well, at least I know this is an exothermic reaction. For the change in enthalpy, again, is the enthalpy of the products or final minus the enthalpy of the reactants or initial. Remember, for the change in volume, going back a little bit, we had volume final minus volume initial. So similar concept here, final minus initial for enthalpy, but the final enthalpy reflects the enthalpy of the products. The initial enthalpy reflects the enthalpy of the reactants. Because the reactants start out at a higher enthalpy than the products, then it's a smaller number minus a larger number. We always have a negative sign for the change in enthalpy for an exothermic process. Now, a number like this for the change in enthalpy, it's still on a per mole basis. Does this mean it's per 1 mole of methane or CH4, or does this mean it's per 1 mole of oxygen? Well, oxygen has that 2 molar coefficient out front. Methane has an implied 1 molar coefficient out front. So this change in enthalpy is this many kilojoules for every 1 mole of methane. As written, this balanced reaction has a 1 molar coefficient out front. So again, this is for every 1 mole of methane. As written, this applies for every 2 moles of oxygen. So let's keep going now and see how we can apply these different signs for enthalpy and these being on a per mole basis. So we saw this value before, so solid water melting into liquid water. Always for these enthalpies, we know this is at constant pressure. When you're given a change in enthalpy value like this, we know it's at constant pressure. That's one of the assumptions that goes into the change in enthalpy value. So for every 1 mole of solid ice, we know it takes 6.01 kilojoules of heat or enthalpy to melt this solid ice into 1 mole of liquid water. Now, an important detail with the change in enthalpy, if you're talking about the reverse of a certain reaction, then the change in enthalpy is the opposite sign. So now we're going to go from liquid water back into solid water. That change in enthalpy is now negative 6.01 kilojoules per mole, where this one originally from solid to liquid is positive 6.01 kilojoules per mole. Then another factor in these enthalpy values, the change in enthalpy values, if you multiply both sides of the equation or reaction by some factor like N, then this was sort of alluded to already, then delta H must change by the same factor, or N. So if we change these to 2 molar coefficients out front, then we take 6.01, and for the whole reaction, we multiply this by 2. Just to show this worked out, see how the units go. So we have 2 moles of solid H2O. We have 2 moles of solid H2O, then moles and moles cancel out. Now we multiply 6.01 times 2, get about 12.0 kilojoules. So again, it's no longer, though, to point out, it's no longer on a per 1 mole basis. These two can still be stated as per mole because this is on a per 1 mole basis. Now we have 2's out front for the molar coefficients. So it's no longer on just a per mole basis. So now we just report how many kilojoules. So we took this multiplied by 2. So we can do any combination. If we have this starting reaction and the starting change in enthalpy, the original change in enthalpy, we could multiply by 4, we could multiply by 3, we could reverse the reaction. So we can do all these different things. We just need to adjust the change in enthalpy value to accommodate for what changes we make. Do we multiply by 4? Then we multiply this value by 4. Do we multiply the molar coefficients by 4? Then we multiply this value by 4. Did we reverse the reaction? Then we change the sign here. If it started out negative, then for the reverse of that reaction, it would be positive. If it starts out positive, then the reverse of that reaction would be negative. Now, we've been practicing incorporating the physical states of matter when we write out balanced reactions. For the change in enthalpy, including the physical states of matter is going to be crucial now. We have to include the physical states of matter. Why? Well, solid to liquid is 6.01 kilojoules per mole, but liquid to gas is a whole other number. So solid to liquid, a certain number of kilojoules per mole, but liquid to gas, a very different number of kilojoules per mole. The properties that cause water to go from liquid to gas look different than water going from solid to liquid or vice versa. Okay, so different amount of heat requirements definitely depends on the physical states of matter. So we are going to include these physical states of matter as we've been doing, but just another reminder, so especially in chapter 6, essentially always moving forward, we want to include these physical states of matter in our balanced chemical reactions. Right, so balanced reactions and of course include physical states of matter. Let's try this practice problem. So a chemist measures the enthalpy change delta H for the following reaction. Use this information to complete the table below. So we have this reaction initially. Its change in enthalpy is negative 69 kilojoules. What is the enthalpy change then for this version of the reaction, this one, and this one? What you might notice is that sometimes these are reversed and sometimes these molar coefficients have been changed. So let's practice taking this amount of change in enthalpy to figure out what these would all be. From what we just reviewed, the reaction enthalpy of the reverse reaction is the negative sign. If it was negative, then it would be the positive value for the reverse reaction. Then the reaction enthalpy for the reaction multiplied by n. So if we took all the molar coefficients, multiplied them by n, then we take the change in enthalpy and multiply that by the same factor n. This one we didn't talk explicitly about yet, but if the reaction enthalpy for the reaction divided by n, so let's say we had all these molar coefficients like 4, 2, and 2, that would not be a simplified balanced reaction though, right? Because these are not all simplified. But let's say we had this, and then we took these and went from 2, 1, and 1. That means we should take the change in enthalpy value and also divide that value by 2 because we're taking all these molar coefficients and dividing also by 2. Okay, so we can change the sign, we can multiply the value through by n, we could also divide the change in enthalpy value by some factor n. So looking at the first reaction now, we notice that it's going from, originally we have C6H12O6 on the reactant side. For this first reaction, now that same molecule is on the product side. Then here, 2CO2, 2CO2, 2C2H5OH. So for this first reaction, all we did was reverse it. Right? We didn't change the molar coefficients. It's still 1, 2, and 2, or 1, 2, and 2. So with the change in enthalpy for the reverse of the reaction, we just change the sign, but we don't multiply or divide by any factor. That means for this first reaction, we should make this positive 69 kilojoules for the change in enthalpy for this reverse of the original reaction. Let's try the second one now. So this still looks like it's the reverse, right? So we have CO2 and C2H5OH on the reactant side. Originally, though, they're on the product side. So we definitely reversed the reaction. We also, it looks like, took these molar coefficients and multiplied them by 2. Now C6H12O6, this had a 1 molar coefficient. Now it has a 2 molar coefficient. These were 2 and 2, now they are 4 and 4. So we need to change the sign and multiply by 2. So that equates to 138 kilojoules. That's for the second reaction where it was reversed and the molar coefficients were multiplied by 2. Let's take a look at the third one now. So it's still in the forward direction, so C6H12O6, C6H12O6. We didn't reverse the direction, so the sign is still going to be the same, but we did something to the molar coefficients, right? So it went from 1 to now 1/2. 2 and 2 are now 1 and 1. That means we need to divide by 2, or it would be the same thing as multiplying by 1/2. So we keep the sign, negative 69 kilojoules, multiplied by 1/2 or divided by 2. That then equates to negative 35 kilojoules as our change in enthalpy for that third reaction. Let's look and make sure that our answers check out. So yes, we changed the sign. Yes, for the second reaction, we reversed it and multiplied by 2. Here we just reversed it. Then in this one, we didn't reverse it, but we took these molar coefficients and divided by 2, or multiplied by 1/2. So that's how we deal with change in enthalpy values for reverse reactions and then when these molar coefficients have been changed. Let's try this topic now. So calculating the heat of reaction from molar reaction enthalpy and the mass of a reactant. To go into this topic, let's start solving this practice problem. So a chemist measures the energy change or the change in enthalpy during the following reaction. Based on this information, we are going to decide, is it endo or exothermic? Big hint, we need to look at the sign of the change in enthalpy. Then we have this many grams of ammonia react. Would heat be released or absorbed? Then if the heat will be released, how much heat will be released, and reporting that in kilojoules. So we should notice right away that the change in enthalpy value is positive. For a change in enthalpy value, we know that is products minus reactants. For an endothermic process, there is an energy gain over the process of the reaction. That means our reactants start out at a lower enthalpy or energy than the products. There's a gain or an absorption of energy throughout the reaction. So then a larger enthalpy or energy value for the products minus a smaller energy or enthalpy value for the reactants. We can arbitrarily say this is something like 5, again, minus 1. Remember, for the change in enthalpy for an endothermic process, it is always a positive value. That means we've answered the first question. It's definitely an endothermic process based on the sign of the change in enthalpy. And as a review here, so this important concept in chapter 6, the principle of conservation of energy, it tells us that 160 kilojoules gained by the chemical compounds can't just appear from nowhere. It has to come from somewhere. If it's an endothermic process, that means that from the surroundings, the system is gaining energy or absorbing energy. So here, that amount of energy must come from the surroundings, which could include the air, the reaction vessel, and so on. So the reaction we're looking at is our system. It gains energy from its surroundings. It gains energy from its surroundings because we see that positive delta H, it's an endothermic process. For an exothermic process, we still think of the reaction as the system, but in that case, it would be giving off heat to its surroundings if it were exothermic and have a negative delta H. So that's for exothermic. Positive delta H is for endothermic. Endothermic comes from Greek for endo is into, and then therm is for heat, so like thermometer or thermal. Then exothermic is Greek for out of. So exothermic, heat is released out of the system. Endothermic, heat is absorbed into the system. Okay, so just another nice reminder on how to think about principle of conservation of energy and endo versus exothermic. So if the reaction is endothermic and we have this many grams of our reactant that is reacting, will any heat be released or absorbed? Well, yes, it's an endothermic process and we have a lot of our initial starting reactant. So for an endothermic process, all we need to be able to answer the second question is the fact that it's endothermic, meaning that heat is going to be absorbed. It's an endothermic process based on the sign of that delta H. Now let's use this mass and try to calculate exactly how much heat will be absorbed by the system from its surroundings in this endothermic process. So from our starting reaction, we know this change in enthalpy value is this many kilojoules. That reaction is based on the fact that in the balanced reaction, there are 2 moles of ammonia gas. So the importance of these balanced chemical reactions comes back yet again. So because of that stoichiometric coefficient of ammonia is 2, then this change in enthalpy, 160 kilojoules, is for every 2 moles of ammonia that react. Now, if there were twice as much ammonia, like 4 moles, for example, we know from what we just reviewed, we would multiply that change in enthalpy value by 2. So then that would be 320 kilojoules. Then similarly, if half as much ammonia, so such as 1 mole reacted, then that delta H we'd have to divide by 2. So notice here that the delta H is not listed as 160 kilojoules per mole. It's not listed as that, it's just this many kilojoules associated with this balanced reaction. That means we can read this as 160 kilojoules for every 2 moles of ammonia, 160 kilojoules for every 1 mole of nitrogen gas that is produced, and 160 kilojoules for every 3 moles of hydrogen gas that is produced. So we know 160 kilojoules for every 2 moles of ammonia. But we don't know how many moles of ammonia we're starting with. We know how many grams are in our reaction. So here we have 97.1 grams of ammonia. We need the number of moles because we know for every 2 moles of ammonia that react, it is this change in enthalpy. Looking at the periodic table, the atomic mass of nitrogen, then 3 times the atomic mass of hydrogen, that comes out to about 17.0305 grams per mole. To orient the molar mass correctly to get moles of ammonia, we'll say 17.0305 grams per mole. So we need to put grams and grams in the correct place so they would cancel out. So again, molar mass down here in the denominator. So this many grams per mole. Then we're left with just moles of ammonia. That calculates to 5.7015 without rounding yet, moles of ammonia gas. So we have this many moles of ammonia gas. We know it takes this change in enthalpy for every 2 moles of ammonia gas. But we don't have 2 moles, we have 5.7015 moles. How do we connect these two now to get the correct change in enthalpy, given actually how many moles of ammonia we have in our reaction? So remember, these balanced reactions just help us connect how many moles of reactants and products are necessary for a complete balanced reaction. In the real world, in the lab, we rarely have exactly 2 moles of ammonia we're starting with. We know how many moles we actually have, and we know this balanced reaction, which tells us how many moles of ammonia are required to produce how many moles of nitrogen. So this just helps us connect these mole-to-mole ratios. But again, we have to consider how many moles we actually have in the lab in an experiment. So now I like to set this up as a proportion. You can think of this in a few different ways. We do know that 160 kilojoules is required for every 2 moles of ammonia gas. You could set this up as a conversion factor as well. So another way to think about it using these ratios is we don't know how many kilojoules for our change in enthalpy for our actual number of moles. And we just calculated that on the last slide. So 5.7, I should say, 5.7015 moles of ammonia gas. To solve for a proportion or ratio like this, we sort of cross multiply. I'm going to call this x. So 2 times x is equal to 160 times 5.7015. This is units of moles. This is going to have to be kilojoules because of the unit here. This is kilojoules, and this is moles. So this x value we determine will be in units of kilojoules. Multiply 160 times 5.7015, then divided by 2. We should get x to be equal to 456.12, without rounding yet, kilojoules, right? That has to be our unit because that's our unit here. We can't just randomly take kilojoules and equate that into joules. We have to match these units here. So to get this into the correct number of sig figs, this is 456 kilojoules. We figured out it was endothermic based on the positive sign of the change in enthalpy. Because it's endothermic and because we are reacting some of our reactant, then yes, as this amount is reacting, some heat is going to be absorbed because it's an endothermic process. Then we calculated this change in enthalpy based on the actual number of moles of ammonia gas. There is a similar practice problem in the main slide deck, so example 6.3. and in your textbook. So it should be the same example in your textbook and in the slides. Again, if you have any questions about any of these problems or the ones in the main slide deck, definitely let me know. I do want to do one more practice problem together, so let's do 6.6. We'll do this one together and one more. So we have this many grams of naphthalene, and it's put into a constant volume bomb calorimeter. We have a temperature increase of the water, and we're told the water goes from 20.28 degrees C, so that's our initial temperature, to 25.95 degrees C. Now we have a heat capacity, not a specific heat capacity, just a capital C heat capacity in units of kilojoules per mole. Remember, for a general heat capacity, mass is not a factor. So we have a heat capacity for the bomb calorimeter. So let's review what we've done. So for Q of the water, we know we can usually say that is MC delta T. We have a specific heat capacity for water, so that 4.184 joules per gram degrees C. Now, because it's a specific heat capacity here, it means we need a mass term to be able to cancel out grams. Then delta T is canceled out, units are canceled out by degrees C, leaving heat in the correct unit of joules. What do we do if we have a piece of data that's not a specific heat capacity, it's just a general heat capacity where mass is not a factor? So for the calorimeter, for Q cal, we don't care about the mass of the calorimeter, so it's not going to include M in the heat of the calorimeter. Instead, all we need for the calorimeter is C delta T. So the heat capacity is in kilojoules per degree C. Change in temperature is going to be in units of degrees C or Kelvin, to where degrees C would cancel out and Kelvin would also cancel out depending on what unit we're given the heat capacity in. That leaves heat in the correct unit of just kilojoules. That means when we have a heat capacity, such as one for a calorimeter, mass is not a factor. Therefore, it's no longer Q equals MCat, it's just Q equals cat. So Q just equals C delta T. We don't need a mass term. So we don't need the mass of the calorimeter if we're just given a heat capacity in units of energy over temperature. Then what are we doing with this information? We're going to solve for the molar heat of combustion. So in solving this, we know the heat capacity and the temperature rise. How do we calculate the heat absorbed by the calorimeter itself? Then what is the heat generated by the combustion of this many grams of naphthalene? Then what is the conversion factor between grams and moles of naphthalene? Well, this one we should recognize as using the molar mass of naphthalene. So to solve for the heat absorbed by the calorimeter, again, we know the heat capacity. What about this delta T? Well, we're told that the water rises from 20.28, I should say, to 25.95. That means the calorimeter is also initially at this temperature and then rises to this temperature. So the delta T for the calorimeter is also the change from 20.28 degrees C to 25.95 degrees C. So you kind of picture the calorimeter, then the water on the inside. These are the same temps. This is not always the case, but what helps us know this from this problem is that the bomb plus the water has a heat capacity as such. So then the water rising from this temperature to this temperature, this is the rise in temperature for the water plus the bomb calorimeter. This question could definitely be written a little bit more clear, though, to let you know that this temperature rise does reflect the material of the bomb calorimeter itself. So let's keep going. Let's solve for the heat of the calorimeter. So again, for a heat capacity that's just in units of kilojoules per degree C, we don't need a mass term. That means we just need the heat capacity of the calorimeter, which we were told is 10.17 kilojoules per degree C. Then the delta T for the calorimeter, we needed to assume it was the same as the change in temperature for the water, so T final minus T initial. To show you how the units work out here, so why we don't need mass. So change in temperature is degrees C, then degrees C and degrees C cancel out. We want heat to just be in joules or kilojoules. So Q or heat to be in joules or kilojoules, so this unit does work out. Now, another point I should clarify is that the heat capacity of the bomb calorimeter plus the water was found to be this heat capacity. That means that this 4.184 joules per gram degrees C for water was already incorporated into this heat capacity value. So we actually don't need to consider just the specific heat capacity of water, just this combination of the water plus the bomb calorimeter material. Then let's figure out what is our system and what are the surroundings. So in the system, we know we have naphthalene that is reacting. In the surroundings now, we are looping in water plus the calorimeter. We just figured out the heat that's absorbed by water and the calorimeter. It's this many kilojoules. Now, as we connect these, we know that the Q of the system has to be the opposite sign of Q or heat of the surroundings. So opposite signs here. We just figured out what's happening to the surroundings. The surroundings are the water and the calorimeter. That means the opposite has to be happening for the naphthalene. So the surroundings absorb this much heat. That means the naphthalene itself must be giving off or releasing this much heat. So Q of the calorimeter or Q of the surroundings, that is the negative sign of Q of the reaction, where the reaction is our system that contains naphthalene. So Q of the reaction or Q of the naphthalene or Q of the system has to be the opposite sign that we just found. So 57.66 kilojoules. This came out to a positive sign because this final temperature was larger than the initial temperature. So larger number minus a smaller number, that came out positive. So this value here is positive. So Q of the reaction, it loses this many kilojoules of energy or heat. Now on a per mole or per gram basis, we know how much naphthalene we put into the reaction vessel. We had this many grams of naphthalene. This many grams reacted to produce or release this much heat. Now in the problem, we are asked to find the molar heat of combustion. Right now we have grams of naphthalene. We need moles of naphthalene to know how much energy or heat was released on a per mole basis. Okay, so it's this many kilojoules of heat that are released. Right now we know is for every 1.435 grams of naphthalene we put into the reaction vessel. But we want this on a per mole basis, so we definitely need to convert grams into moles. Going to the periodic table, looking at the mass of carbon and hydrogen, there are 10 carbons and 8 hydrogens, so then that molar mass is 128.2. To be able to cancel out grams and then just have moles in the numerator, this is 128.2 grams per mole. So you could solve this all together or first convert grams into moles. So if we did that, we'd have this many moles. Then we're dividing this amount of heat or energy by this many moles. So we want to know the energy per 1 mole. So this much heat was released, but we didn't just have 1 mole in our system. We had less than 1 mole. So we want to know how much energy per mole, per 1 mole. So if we divide kilojoules by this value, we'll get negative 5.151 times 10 to the third kilojoules per 1 mole. That is the answer we were looking for. This answer that we just calculated is our molar heat of combustion. So our molar heat of combustion, how much energy or heat combusts for every 1 mole of our reactant. So enthalpy of reaction, sometimes called heat of reaction. This is table 6.3 in your book. Here are some examples of various heats of reaction. From this table, some important reminders. We must have a balanced chemical reaction, of course, and we have to include those states of matter. Solid to liquid is a different enthalpy of reaction or heat of reaction compared to liquid to gas, for example. So balanced reaction and the states of matter are important. The other takeaway from this table I want to point out is that the different signs for delta H. What does that negative sign mean again versus a positive sign? So negative heats of reaction or enthalpies of reaction, we know those are exothermic processes, whereas positive heats of reaction are definitely endothermic processes. You'll be provided with enthalpies of reaction that you need. You don't need to worry about memorizing any of these or writing any of these on your note card. So you'll be given these values that you need. Let's do another one together. So then example 6.8, we have some quantity of hydrochloric acid is mixed with sodium hydroxide. So don't forget about our acids and bases here in a constant pressure calorimeter of now negligible heat capacity. That means we're not going to be worried about the heat of the calorimeter. It's at a negligible heat capacity. That means we're only going to care about our reaction as our system, and our surroundings are not going to include the calorimeter. It's going to include likely an aqueous solution that this reaction is taking place in. So this is taking place in a certain molarity of hydrochloric acid with a certain molarity of sodium hydroxide. That means our solvent here is what? So to make this, we could take solid sodium hydroxide and then dissolve that into water. So our surroundings here are going to be the aqueous solution that contains this concentration of hydrochloric acid and this concentration of sodium hydroxide. So we have the initial temperature of the acid and the initial temperature of the base. Both of them start out at 22.50 degrees Celsius. Then we have the final temperature of the mixed solution. So it sounds like they both end up at the same final temperature, which also makes sense. So they're in the same reaction vessel, so they're going to equate and reach a thermal equilibrium, reaching the same final temperature of 25.86 degrees C. Now we have this reaction. We should make sure it's balanced. So here we have 1H, 2H, here's 2. Oh, we have 1 and 1. Calculate the heat change for this neutralization reaction on a per mole basis. What does this neutralization reaction mean again? Well, we're taking a base, a strong base, with a strong acid. We are forming water and a salt. So we can assume the densities and the specific heats of the solutions are the same for that of water, so that 4.184 joules per gram degrees C. Is this a specific heat capacity or just a heat capacity? Well, definitely this is a specific heat capacity, right? Because it has that gram term. Then the density is 1.00 gram per mil. So we'll use this density for water as the same for our solutions. To approach solving this, because the temperature rose, the neutralization reaction is exothermic. So if we took some vessel of acid and some vessel of base, we mix them together, we're told the initial temperature of the acidic solution and the initial temperature of the basic solution. When those get mixed, the temperature increases. That means we know that heat or energy is being given off in the reaction. These two reactants come together and heat is released. This is an exothermic reaction. For an exothermic reaction, do we write energy on the product side or on the reactant side? For an exothermic process, energy is released, right? So we could go back here and technically add on energy to this balanced reaction when we're thinking about this in terms of being an exothermic reaction. Energy is on the product side. Energy is released for an exothermic reaction. Then we'll need to calculate the heat absorbed by the combined solution. What is the heat of reaction? What is the conversion factor for expressing the heat of reaction on a molar basis? So again, molar basis, this means we're going to write this in a per 1 mole basis. So some value for heat or energy per 1 mole basis. So let's define our system. It's going to be the vessel that contains the acid and base once they're mixed together. So in our case, we're considering the reaction itself. So what's happening on the molecular level here with acid and base reacting together. Then whatever's happening on the reaction scale, we're going to tell based on the rise in temperature of the solution that contains the reaction. So our reaction itself is the acid plus the base. The acid and the base aren't all that's present in the solution. So then we also have our surrounding solution that includes the water that surrounds those acid and base molecules. Remember, the acid itself is hydrochloric acid. The base itself is the sodium hydroxide. We are not just focused on the acid and base molecules in solution. We also have water that's present. Then we are reading the temperature change for the water, for the solution. We're going to make connections about the change in temperature of the water to what's happening with this acid-base reaction on the molecular level. So let's figure out what's happening for the solution. For the solution, we want to think Q equals mc delta T. We know the change in temperature, or we can calculate that for the solution. Now, what about the specific heat capacity and the mass of the solution? Well, we're told we can use the specific heat capacity for water for our solution, so that's going to be our value for C. Now, what about the mass of the whole solution? Well, this should say mils, so we have 1.00 times 10 to the 2 mils of acid, and we have this many milliliters of the base. If we have this much volume of the acid and base that are combining together to form our solution, we can get the mass of the solution by using the density of water. So from scientific notation, we move this over 2 times. That is 100 mils of acid and 100 mils of base. Altogether then, the solution is 200 mils of HCl and NaOH, so 200 mils together. How much does that weigh? We're told we can assume the density for water for our solution. So if we have 200 mils of solution, using the density, we're going to say 1.00 grams per mil, and we write it like this, so we can cancel out mils and mils. So that total mass then is 200 grams of the solution. Let's plug in now the change in temperature, the specific heat capacity of the solution, and the mass now of our solution. Then we'll connect that to the heat of our reaction, where the reaction is truly just the acid plus the base reacting. So Q of the solution is mc delta T, same thing to say ms delta T, Q equals m cat. Delta T is T final minus T initial, so we plug in these two temperatures here for delta T. The specific heat capacity of water and for the solution is 4.184 joules per gram degrees C. Then this mass again is 200 grams. So this many grams, let me show you how the units work out. So grams for the mass, specific heat capacity is joules per gram degrees C. The change in temperature is degrees C. Then grams and grams cancel out, degrees C cancel out. we leave just joules for the heat of the solution. Now, we couldn't just solve for Q of the reaction right away because we don't truly know the specific heat of the acid plus the base that make up our reaction. We can figure out a specific heat to use for the water, the solution that surrounds that reaction. So again, we're taking information about the solution to find out information about our reaction. Right now, we just went through and solved for the heat or the energy of our solution in joules. Because the heat of the solution is this many joules, it absorbed this many joules from the acid and base that are reacting. Then the reaction itself, so Q of our reaction that involves the acid and the base, we have a negative sign now, and we can convert this into kilojoules. It's not necessary that we convert this into kilojoules, but if we're asked for our final answer in kilojoules per mole, then we should convert this. And definitely that negative sign now, because whatever heat is made from the reaction or released from the reaction is then being inputted into the solution. So the solution gained this much heat, the reaction itself lost this much heat. So 2.81 times 10 to the third, that's moving the decimal point over 3 times, 2810 joules. There are 1,000 joules in 1 kilojoule. So now we know the reaction itself lost this much heat or released this much heat. It released this much energy in the form of heat. So now we know how many kilojoules, but we need this on a per 1 mole basis. So this will be a good review on molarity. Remember, capital M, molarity is how many moles per liter. We need to know how many moles so we can divide that number of kilojoules by the correct number of moles. Going back to our reaction, we have 1 mole of NaOH for every 1 mole of HCl. When we report the heat on a per mole basis, we can say for every 1 mole of NaOH or for every 1 mole of HCl. We don't need to add moles of both because, again, this is just on a per 1 mole basis. For all these heats of reactions and enthalpies of reaction, remember we're just looking at that in terms of one of the reactants. It's how much energy or heat for every 1 mole or per every 1 mole of a reactant. So as long as these both have a 1 molar coefficient out front in this balanced chemical reaction, then we can say for every 1 mole of NaOH or for every 1 mole of HCl. This also works out because we have this many mils at this molarity of HCl. We have the same number of mils and the same molarity of sodium hydroxide. Let's take this volume and the molarity and figure out how many moles. Remember, capital M is molarity. That is moles of solute per liter of solution. Hopefully you are still remembering molarity. This will be a big important concept in chapter 6 as well as what we saw previously in chapter 4. Molarity will always come back, essentially, especially in this semester. So we have this many moles of solute per liter of solution based on the given molarity. So both of those were listed at 0.500 molar. We can think of that as 0.500 moles per liter. Now, how much volume was there? Well, we had this many mils. We're going to need to convert that into liters. So moving this decimal point over 2 times, this is 100 milliliters. Let's convert this into liters. There are 1,000 milliliters in 1 liter. Then mils and mils cancel out. Then we have this in terms of liters. So that comes out to 0.1 liters. Now to find how many moles, we need to take the molarity, that's in terms of moles per liter, multiply it by the volume, so the liters cancel out. Remember, we had to convert this mils into liters, though, to make these units work out. Molarity is moles per liter. So 0.5 moles per liter times this many liters, this much volume, we get this many moles. This is true for NaOH and for HCl. And we just want to prove the per 1 mole basis for one of the reactants. So it has to be on a per mole basis, but just for every 1 mole of NaOH or for every 1 mole of HCl. So we figured out this many moles are actually reacting of either NaOH or HCl. From the last slide, we calculated this many kilojoules, negative kilojoules, is the heat lost from the reaction, where the reaction involves the acid and the base in the surrounding aqueous or water-based solution. So we want to ultimately find the heat change for this neutralization reaction on a molar basis. We know the heat, now we know how many moles were involved. We take this many kilojoules divided by moles to get this answer on a per mole basis. This is an important one to think about. Is the sign consistent with the nature of the reaction? This is a negative heat. If it's a negative sign for the heat of reaction, yes, that makes sense because these mean we have an exothermic reaction. This negative sign means we have an exothermic reaction. We're at the end of this part of chapter 6 now. Please, as always, let me know if you have any questions, if I can help with any practice problems in office hours. Hope you're all doing well, and I will talk to you soon.